Hello and welcome back to the shop. Today we're going to work on some parts for the billet build. So I ordered up some AN fittings to go on the top of the case. These are for the crankcase ventilation. This is a -10 to M18 by 1.5 and then a -8 to M14 by 1.5. So these guys thread into the top of the block, and then we can use AN hoses to connect to the crankcase ventilation. Next, let's see. So I also ordered from Outfront Motorsports a -10 AN little adapter that goes on the back of the head for the oil drain. Normally the head has a pipe that sticks out you clamp a hose to. And so we're gonna grab this guy here. I'm gonna put a cap on it so I won't mess up the threads if I have to tap it at all. And we'll get this guy installed over here so it fits right into the back of the head. Let me just push in. Yeah, it did, there we are. And then there's a nut that locks that in there. All right, I'm gonna give that a little tap. Ah, nice. Okay. All right, we have a nice -10 AN fitting for the oil drain. Let's see what else we have here. So for the fuel pressure regulator, I'm going to be using this Perrin fuel pressure regulator, which I like a lot, and there are a couple reasons why. The first is that most regulators usually have either 2 or 3 ports on them, and typically you have the fuel coming from the pump to the fuel rails, then into the regulator, and then from the regulator back to the tank. And of course the regulator is regulating the amount of fuel that it allows to flow back to the tank to keep the pressure on the other side constant, or at least offset based off this little nipple here. And so they work great. In the case of most Subarus, you typically have 2 fuel rails, which I do. And most people on high horsepower applications usually do a parallel setup. So they'll feed both sides of the fuel rail and then have the return side coming up here and go to the regulator. And when you do that, normally you end up having to use little Y adapters to take the 2 lines and put them into one to go to the regulator. And it certainly works. In fact, my previous config had that set up, but it's kind of messy and it makes it difficult to route the lines only because this angle, either 45 or 90, makes it a little bit unwieldy. And so the Perrin regulator is cool because it has the input feed from the pump and the return to the tank. And then it has 4 fittings on the other side, 2 to the rails and 2 from the rails. So you can go directly from the regulator to the rails and back without any Y adapters. And so it makes it a really nice package. If you bolt this onto the manifold or something like that, you can make a really clean, sort of self-contained install. And it's a great regulator. It has one other feature that's interesting, which is that you can take it apart, and I have one here. And normally this little diaphragm with the ball there goes over top of here, and this ball seats against a little fitting that gets attached there. And this is what is used to regulate the fuel return. But what's interesting is that it comes with 3 different fittings with 3 different size holes in the little adapter. And the reason for this is to allow you to do a little bit of fine tuning depending on your setup. If you have a fuel pump that, or a fuel setup where you have like 2 fuel pumps that are on full flow all of the time, then at idle you'll have a lot of your fuel getting returned. And in that case, you can use one with a larger hole in it. If you have a stage setup where at idle you only have one of the pumps turned on and maybe running at a lower voltage, then you can typically use the smaller holes. It allows you to sort of fine tune the response a little bit. I've generally found that using the larger hole works in most cases. So in my case, I have it set for that. But it's a little extra feature. So we're gonna get that guy installed here in a bit. I also got some radium fuel pulse dampers. And these go right into the fuel rail. These are the ones designed for up to 70 PSI of base pressure. They make ones that'll go to a higher rating, but they're quite a bit bigger and that may have trouble fitting in there. So in this case, these thread onto the bottom of the fuel rail and we'll index it so that the connection kind of pushes out a little bit. And then also on these fuel rails, these are IAG fuel rails. They are -8 ORB ends, and so I got some -6 AN to -8 ORB, and so I will install all of these guys and get these guys all configured and ready to install. So we'll come back and do that in a minute. So let's talk a little bit about oil cooling. The factory setup for oil cooling, the factory turbo cars have this heat exchanger that is attached to the block and provides heat exchanging between the coolant and the oil. So it acts as both a cooler and a heater, and it actually sits on the block sort of like this and connects to a fitting there, and then the oil filter goes on the top of that. And if the oil temperature is lower than the coolant temperature, then it'll heat the oil up, and then obviously the reverse is true in the other direction. But it doesn't really do much to cool the oil. All it does is raise the temperature of the coolant quite a bit if the oil gets pretty warm. So we are going to not use this. Instead, I like to use a real oil cooler. And of course, this is the default setup pipe made for that heat exchanger. And so you can order from Subaru the adapter used on the non-turbo 2.5 motors. And this guy just threads right in to the block here. And then we can use a regular adapter. So this is a Mocal thermostat controlled oil cooler adapter, which threads on here. And then we can put an oil filter on the end of this. And then we can run these lines to an oil cooler on the front of the car. And so we'll use this to try to get a little better overall control of oil temperatures. But it's an easy upgrade if you're building a high horsepower motor to do this and remove that factory oil heat exchanger. So as far as oil pumps go, I have a new 12 millimeter oil pump and a new 11 millimeter oil pump. And after talking with Chris at Killer Bee and a few other people, Clark and the guys at IG, I'm going to use the 11 millimeter factory 08 dual AVCS pump. I will take this one apart probably in the next video and check to make sure that the bypass is working and smooth. Maybe do a little bit of relief work on a few of the passages just to smooth it up a little bit. Primarily just to make sure everything's set up okay, because you don't want to start the engine with an oil pump not working. A lot of people look to use the 12 millimeter pump, but a lot of testing has shown that it ends up activating the bypass pretty early, which produces a lot of turbulence, which can cause air bubbles and then problems in the oil supply. And this pump can drive enough pressure if done set up properly to work fine. So we're going to use the 11 millimeter pump. I'm not going to adjust the shims at all. And we think that'll work pretty well. So we'll also take a quick look at the head sealing design we're going to use on this. And so you can probably see the sleeves have been machined with a groove, and the gaskets came with these steel O-rings that actually sit down in the groove like that, and then the gasket goes on top and actually goes around the steel rings, and these steel rings just stick up slightly above the dimension of this when the gasket's compressed. So these will push up against the head to provide a sealing surface. So it's similar to an O-ring, but in this case, since the actual sleeve has been machined down, the ring itself will sort of lock into place. So even if there was a bit of lift, it would be almost impossible for the ring to push out or to break out. And so we believe this will provide a pretty good sealing surface for a high horsepower, high pressure application. All right, let's grab a measuring tool. All right, so grab a caliper over here. Okay, let us set the inches, make sure it's zeroed. I have a little gauge block here. Do a little calibration. Oh, 0.1250, that's right on the money. All right, good to go. Okay, so we'll start measuring the thickness of this guy here, the steel ring. 76. So 76. So 76 thousandths. And the groove, let's see if we can measure this very easily this way. 24 thousandths. Let's try that again, a little there. Give a rough idea. About 23.5, 24 thousandths. So we'll call it about 24 thousandths is that groove depth. And then the gasket, let's see here. 51 thousandths, approximately. This is uncompressed, so I have to compress it to get a better gauge of how that's going to sit. 48 thousandths there. But it gives me a rough idea of the size of the groove relative to the steel O-ring.